everyone. Welcome back to the latest lecture session. In the last couple of sessions, we discussed sedimentation in some detail, and in sedimentation, we removed the suspended particles, right? And then we mostly have the dissolved organics and some suspended particles, but we are not greatly concerned about that because they will be removed subsequently. So now our focus is on degrading or removing these organic particles that are dissolved or are soluble, let's say. So because they are dissolved, right, you can't really change phase. As in earlier, what were we doing? We had the suspended particles and we were changing phase, as in earlier they were in water or aqueous phase, and we removed them to the bottom, and more or less they are called sludge, and with dewatering and treatment you can take care of that. But here the organics that we want to degrade, let's say, are what is it now? Soluble and thus dissolved. So how do I do that? I can't really settle them out or such, let's say, right? So here the aspect is that we are going to use microbes that are present out there. So here we are going to look at biological treatment. That's why we call that biological treatment. So in this session we are going to cover these aspects. So obviously, what is the general strategy now? As in, I can let the wastewater stay there and without the microbes just provide a lot of oxygen, and maybe that will take a few years or months, if not years, months, and then I will be able to treat the water. But for that, if I am going to have to aerate water for a lot of time, my tank volume size will be a lot, let's say, right? As in, I know that theta is equal to V by Q, right? So you know flow rate is constant. So if theta is high, then the volume of the tank also will have to be high. So that's not going to be feasible, and also providing oxygen for a lot of time, that's not an feasible option too because of the cost. Another aspect is what do we say, putting in a lot of oxidizing agent. Again, that's going to be costly. So what are we going to do? We are going to try to mimic what nature typically does, right? What does nature facilitate? It facilitates microbial growth, and these bacteria degrade the relevant wastes, let's say, or our wastes, let's say, right? So we are going to promote that. How do we promote that? We promote that by creating conditions that promote bacterial growth, and also by increasing the concentration of the microbes in this wastewater. So that's what we are going to discuss, or that's the general strategy. So obviously, for the microbes, what do they need? They need sources of energy. Why are they degrading it? Well, they don't have any sense of smell, and they don't really like wastewater due to its smell or such, right? They degrade the waste or our waste as their food, or consider them as their food, because they gain energy from it and then can synthesize new cells, let's say, right? So energy sources. To synthesize new cells, what is it that they need, let's say? Similar to us, they also need nutrients. We will discuss that. And what about the general environment? As in, we, I guess, are can be stressed. You know, we do have our own peer pressure and relevant issues, work pressure issues, but we are always concerned with the environment, you know, too hot, too cold, let's say, right? And these kinds of environmental conditions. Similarly, microbes also have environmental conditions, let's say pH, temperature, and so on and so forth. We will look at that. And then based on these fundamental aspects, there are different modes of treatment systems. We will briefly touch upon some, but discuss activated sludge process in greater detail, because that's the most widely used form of wastewater treatment out there, right? So let's move on here. So biological treatment, what are we trying to do? We are trying to, what do we say, see to it that the waste, which if I leave it out there, can lead to septic conditions, smell because of, what do we say, reduced forms of sulfur like hydrogen sulfide, let's say, being given out. Explosive gases like methane can be given out, and then you are going to have, what do we say, flies and such because of septic conditions and such. So you don't want to have that. You want to have a relatively stable compound, and we are going to get to that by using microorganisms which release enzymes, let's say. Again, our main aim is to degrade the organics, but by promoting the growth of microbes, let's say, right? So let's move on. So sources of energy, let's say, with respect to microbes or microorganisms, we are looking at a source of energy or general source of energy. So we can classify them as chemotrophs or chemotrophic and phototrophic. Obviously phototrophic, photo, right? So the source of energy is light, let's say, source of energy is light, but we are not concerned with that though. If what do we say, algae or such, typically what do we say, are dependent upon what do we say, light or photosynthesis, we are not really concerned with that because that's of no use to us, right. So here let's say chemotrophs, let's say chemotrophic as in the sources of energy or chemical sources of energy. This is what, or these are the microorganisms we want to make use of. So what is it that we do? For example, BOD or the waste or our organic content, or our waste or the organic content, which is measured by BOD, can be removed in the presence of oxygen or oxidized in the presence of oxygen, right. So thus we are going to use for our waste removal, let's say. Another aspect is we also give out ammonia, let's say, and this is also, as you can see, a reduced form of nitrogen. And again, we have oxygen as an electron acceptor and nitrification will take place. And organics plus nitrate, here the electron acceptors were oxygen and oxygen, right. Here the electron acceptor is nitrate. We will discuss this in greater detail. As in from here we will get NO3 minus, but NO3 minus is very soluble in water and you do not want it in water because it leads to what do we say, adverse effects in humans and certainly in the aquatic systems too. So once you convert this NH3 into NO3, you want to remove this from water. How do you do? You by promoting what we say, formation of nitrogen gas, pardon me, right, and that is called denitrification. First one is nitrification and then is denitrification, as in we are changing this from the aqueous phase water to the gaseous phase, thus nitrogen is leaving our system. So sources of energy. In this context, one aspect to understand, or another aspect is that we have heterotrophs, hopefully my spelling is right, and autotrophs, let's say, okay. So one depends upon organic compounds or organic sources of carbon and the other on inorganic source of carbon, namely carbon dioxide, let's say, right. So obviously as you can see, this is what do we say, with respect to heterotrophs, or done by heterotrophs, let's see, right. And then nitrification typically by what is it, autotrophs, so chemoautotrophs, let's see. Again, you need to, no need to mug up anything, but for the serious listener or such, I am just providing some information. So biological treatment, let us just understand what typically happens. So casein, a kind of protein, I believe, right, we have it in the dairy waste, let's see, right. And here what are we trying to do? We are trying to oxidize it, but again, as I said, the kinetics, as in the rate at which this reaction goes through, is probably not good enough for practical oxidation by just oxygen. So what are we going to do? We are going to introduce bacteria which release enzymes. They release enzymes which act as catalysts, as in they fasten or improve the kinetics of the reaction. So here there are two aspects. One aspect is new cells, as in reproduction, as in new microorganisms are formed, so cell synthesis, and then while transforming it into other what do we say, byproducts, they gain energy. So then again they need the energy, I guess, right. So two aspects, one for energy and one for cell synthesis. And obviously as you see, these compounds are relatively stable. Carbon dioxide leaves the atmosphere, we have byproduct of water, NH3, which if required we will degrade further, right. So energy is required for creating new cells, let us say again, right. And how do we get that? For example, we have redox reactions, explosions, explosives and such, let us say, right. And how there are two aspects there, sudden release of energy and also sudden change in volume. But how is this energy being released? Because there is an oxidizing agent typically, let us say, and a compound that is relatively reduced. So you have a redox process, reduction and oxidation occurring, and then you are going to have transfer of electrons from the reduced compound to the relatively more oxidized compound, and thus you are going to have a redox process and thus release of energy. So that is the same principle here. Here obviously the oxygen is the electron acceptor or the oxidizing agent, and the relatively more reduced form or the compound is this particular waste or R waste, let us say. You see this carbon, that is typically the electron acceptor, let us say, right. As you can see, it is bonded with H, right, and here carbon is relatively oxidized, let us say, right. So that is something to keep in mind. So let us move forward. So here we looked at electron acceptor, right. Let me just write that down. What is it that typically happens? A, which is relatively more oxidized, gains electrons and goes to its more reduced state, right. Here it is more oxidized and here it is reduced, right. For example, here the example is, I guess, O2, right. O2 oxidation state is 0 and it is gaining electrons and going to H2O, where the oxidation state is -2, right. Oxidized form of oxygen, reduced form, let us say. And similarly, let us say for the redox process to go through, somebody has to, or some compound has to take this electron. So, who will take this electron, let us say, right. So, you will have, or who will give this electron, pardon me, that was minor error there. So, here for this oxidized compound to be reduced, somebody has to give the electron. So, you need an electron donor, let us see, right, you need an electron donor. So, who is the electron donor? As you can see, it is this waste or R compound, let us say, right. So, the reduced or B, let us say, B which is reduced will go to the more oxidized form and give out electron. So, this electron will be used by this particular half reaction there. So, we have two half reactions. So, here what is the reduced form? It is the casein, I guess, and this is the reduced form. And what is the oxidized form? As you can see, it is carbon dioxide, let us see. Oxidation state here is, what is it now? +4. So, you can look at what the oxidation state of carbon is in this particular compound. So, this is the general aspect. So, for wastewater, for representation purposes, general, what do we say, based on general ratio of carbon, hydrogen, oxygen and nitrogen, this is the value. But again, there is no one particular, what do we say, value, not value, compound or such that we can use as being representative of all the kinds of wastewater. That is something to keep in mind, right. So, from this redox process you can gain energy, but as we mentioned, there were two aspects. Let us see if we have that, okay. So, there are two aspects are, one is synthesis of new cells, right. I mean, the cells or such won't come out of thin air, right. So, you are going to have breakdown of this particular compound and have formation of cell synthesis. You can look at the stoichiometry, but we are not going to go into that detail, right. So, energy generation, again different fraction. Now, oxygen is the electron acceptor, and then you have the relevant byproducts, let us say, right. So, two aspects out here, we broke down that equation into two aspects. Here for each reaction here that we are going to have two half reactions. Let us look at that. So, for cell synthesis, the donor here, let us say, right, again the donor, electron donor, it is giving out these electrons, let us say. In that process, carbon is being oxidized, right. So, you can check the oxidation state of nitrogen and such, but primary focus here is carbon, let us say. Carbon here is relatively more reduced, and by giving out electrons, it is going to a more oxidized form, let us say. And these electrons, who is accepting that? So, again, okay, so I guess we have some error out here, okay. So, okay, it is 20 H plus, I thought it was an error, so that is right, 20 H plus. These electrons again are going to be used for cell synthesis. Carbon dioxide is again the electron acceptor, let us say, right. So, because when we club the two half reactions, then we do not see these relevant aspects. But this role of electron acceptor is more clear when we look at energy, let us see. So, what is the electron donor? It is still the relevant wastewater or R waste, and we see electrons being given out and the more oxidized form. What is the electron acceptor? It was oxygen, and that is what you see. Oxygen going from 0 oxidation state to -2 out here by taking up these electrons, let us say, right. So, that is what we see out here. In this process, the energy is released, which I guess is again used in this particular reaction, let us see. So, there are different, what do we say, electron acceptors that you can use to, what do we say, achieve different objectives. So, let us just look at some of the different electron acceptors. Okay, so I guess I skipped one other aspect. So, if I club these reactions such that there is one electron on the right hand side of each equation. So, cells, you have this, and the donor case you have this for cells and for the donor, and the terminal electron acceptor you can say is going to look something like this, but again we do not need to go into this detail here. So, as I mentioned, we can look at different electron acceptors. Typically the most what do we say, widely available electron acceptor is oxygen, as we see out here. So, here we have glucose. and glucose being oxidized to form carbon dioxide and water. And here we see 2880 kilojoules per mole of glucose, that is the energy that is released, let us say, right. And if it is in denitrification, the electron acceptor is not oxygen, but as I mentioned, the electron acceptor is NO3 minus. And so, what do we see here? We do see, similar but not as high what do we see amounts of energy as in the case of aerobic oxidation. Why do we say aerobic? Obviously, because oxygen is there. Here there is oxygen, but it is not in the form of what do we say, free oxygen, if I may say so. It's the electron acceptor is NO3 minus. So, these conditions we call as anoxic, right, anoxic conditions. There is still an electron what do we say, acceptor in the form of oxygen, if I may say so, not oxygen. Let me not make it more complicated. Here we have oxygen and the electron acceptor, but not oxygen. We call it the anoxic conditions, let us say, right. And then you have different other what do we say, electron acceptors. Sulfate out here, right, and sulfate is reduced to hydrogen sulfide and less energy, as you can see. Methanogenesis, let us say, right, and fermentation, where you do not have what do we say, an external respiration mechanism here with respect to the cells. But as you can see, as we look at different electron acceptors or fermentation and such, we see that the energy being released decreases. So, microbes, again similar to us or human beings or the students, they do not want to take my class because they need to go through a lot and need to submit a lot of what do we say, heartbreaking homeworks. So, they will take the path of least resistance. They will go to the relevant person who will give easier grades with lesser work, right. So, again microbes too, they want more energy, right. So, typically I guess looking at this analogy, let us say, right, layman's analogy, we see that typically aerobic oxidation is preferred. Only when there is no oxygen will this denitrification take place, right. So, that is something to keep in mind. And when there is no nitrate, only then if there is sulfate will this reaction go through. Again, different microbes are going to be prevalent at each what do we say, are going to carry out each of these reactions. Again, why do they do that? Because they want to get this energy. That is something to keep in mind. So, what else do they require? One is energy, which we just looked at, and different electron acceptors lead to different amounts of energy. And synthesis requirement, what do they need? Similar to us, they need nitrogen and phosphorus. We typically take in nitrogen in the form of amino acids or proteins, let us say. And other nutrients are also required, sulfur, sodium, calcium and so on and so forth, but they are required at much lesser concentrations compared to nitrogen and phosphorus, let us say, right. And suitable environment, similar to us, they want reasonable temperature, moderate pH, right. They do not like too much salinity, total dissolved salts should not be too high, obviously water. And again, if you have toxic compounds coming in along with the wastewater, they are going to obviously affect the growth of your microbes. They can do the job, but maybe not as efficiently and they do not thrive as much. So, they do not like a lot of toxins to be present in the relevant environment. So, types of treatment systems. One, as we mentioned quite often, was activated sludge. We will look at a video 2 sessions down the line. And earlier, when the concentration and also the flow rate were relatively less and land was available, people used to look at aerated lagoons and stabilization ponds, but we will not look at that now. People are phasing that out, at least in India, let us see. So, the key difference between this kind of system and this system is that here we have suspended, as in if this is my tank and this is the water. So, the microbes are suspended, right. So, here they are attached, but attached onto what? Some media. For example, I can provide a media, right, upon which the microbes can grow, right. So, attached growth, let us say, right, suspended growth and attached growth. More often than not, people have been looking at activated sludge process, which is suspended growth of microbes, but sometimes people also look at attached and suspended growth to increase the efficiency, let us say, right. That is something to keep in mind. So, activated sludge process, again, why do we call that activated sludge? Let us understand that. So, I do have a relevant schematic here, we will come back to that. My wastewater is coming in, this is after the primary sedimentation. What does it have? It has a lot of organic content, which I am going to call substrate, which is my waste and the what is it? The food for the relevant microbes. but the concentration of the microbes in this relevant sewage or wastewater, which I am going to represent by X, is going to be less, right. There are going to be some, but not enough for what we say fast degradation, and also the kind of microbes that are present might not lead to what we say the degradation of the kind that we are looking for. So, what am I trying to do, or what do I want to do? I do not just want this X, I need a X that is remarkably high. So, this is X naught and S naught. I need a concentration of X or the microbes in my tank to be very high. So, how can I achieve that, let us say? So, I need a source of microbes, right. So, I need a source of microbes, okay. Let us see where this will come from. So, in this tank, what else do we need to provide? I am going to provide mixing and I am going to provide oxygen. So, here I am going to provide conditions such that the microbes thrive and the concentration is high. Once we stop aeration, we send that to what is called a secondary clarifier or secondary sedimentation tank. What happens is, if we maintain the right conditions, the kind of bacteria that form here are what we call flock forming bacteria with some filamentous bacteria. So, we looked at this figure, I think, in what do we say, the last session, where we looked at the microscopic pictures, right, and we saw the flocks being formed along a filamentous backbone, let us say, right. So, these particular flocks or kinds of microbes, right, they are going to settle down, and they are going to settle down at the bottom. So, typically you can waste it, or you can recycle that, R for recycle, such that when it comes into, okay, I should not draw it here, maybe I should draw it right here. I can recycle it such that the concentration of the microorganisms in this tank where the actual reaction and degradation takes place is pretty high, right. So, that is why we call that activated sludge, as in this sludge which has the microbes, activated sludge is reused, right, activated sludge process. Again, that is what we have, that is the relevant schematic out here. Let us move on. So, I believe we already looked at this. So, why recycle? Loss of microorganisms, right, you can't keep bringing them and you want to increase the concentration, let us see. So, we will skip this. And what are we trying to use it? Obviously, depending on the design, you can decrease the organic content, which we are measuring by BOD. If the ammonia content is high, you can design it such that nitrification first, as in NH3 goes to NO3 minus, and then with the denitrification, this is aqueous phase, and now nitrogen, which is in the gaseous phase, will be formed. This is nitrification, then denitrification, because we are forming nitrogen gas, which will leave the aqueous phase or the water, right. So, we can look at the relevant aspects. So, aerobic BOD removal, nitrification and such, we can achieve that. So, activated sludge aeration, I guess another picture out here. We already looked at this in detail, but again the primary aspect is this return activated sludge. One aspect to note here is that in India, people do not maintain these what do we say, clarifiers, or maintain the right recycle, right. What does that lead to? That leads to very low concentration of the microbes in this particular aeration tank. So, what happens when you have less concentration of microbes? First, the kinetics, right, as in let us say there is 10 kgs of laddu and let us say 100 people, faster consumption, let us say within maybe 10 minutes or so. But if there is only one guy, obviously it is going to be an issue, as in the time or the kinetics are going to be pretty slow. So, same case here, people do not maintain the right conditions for the microbial growth, or do not maintain sufficient concentrations of the microbes. So, that is why different treatment plants, either industrial or sewage treatment plants in India, are typically affected, let us say. So, that is something to keep in mind, right. So, I guess I have one video, you can look at this video, okay, which looks at different aspects, and I will play, or I will try to play another video that is out here. So, you can look at the link and such and the reference. Obviously, we are just trying to look at the schematic, let us see, right. So, process, what do we have? We have the grit chamber, right, or the screens, pardon me, coarse particles, rags and such, then the primary sedimentation basin, right, and then you have the primary sedimentation basin out here, right, grit removal, primary sedimentation basin, and then we have mostly only the suspended matter. And here this, I hope you can see the arrow. We have the biological process where air is provided, microbes are coming into the picture, that is why the biological process, and then the secondary clarifier or secondary sedimentation tank, let us say, right. Let me just play this a bit further. Okay, so what we just mentioned out here. And in the biological process, what do we see happening? What do we have? We have our waste fecal matter, we provide the relevant microbes, right? And then microbes are what do we say, going to degrade the organic matter to the relevant byproducts, let us say, right? But what do they need? They need an electron acceptor, which is oxygen. That is what we are providing here, right? And then, so what do we have here? We have these microbes or flocks that come into picture here. Here this author or the video maker says we add flocculants, but in wastewater treatment we rarely favor or never add flocculants. The kind of bacteria that are going to be formed, if we maintain the conditions to be good, they are going to see to it that this particular sludge settles down, and some will go to waste and some is recycled back, so that the concentration of the microbes in your relevant aeration tank is high enough, let us say, right. So, that is why we call it as activated sludge. The sludge which is activated is recycled and used out here, let us say, right. So, that is enough for now, but you can look at the other video which is not a schematic, but from a relevant treatment plant, let us say, right. So, let us move on. So, what are some of the major biological processes that we try to use, let us say. So, as we looked at in the class or sessions beforehand, we want to look at those compounds which have or exert an oxygen demand, or the organic compounds which exert an oxygen demand, right. So, this oxygen demand we were measuring by BOD. So, we want to remove the BOD. And also we mentioned, algal growth and such. So, we want to remove the nutrients depending upon the concentration. So, we remove nitrogen by nitrification and then denitrification, and then we also look at phosphorus removal. Let us just briefly look at the relevant aspects out here. So, nitrification, I guess we already looked at aerobic BOD removal in considerable detail. Let us just look at nitrification and denitrification briefly, and then phosphorus removal. We will come back to this later, but again we are just understanding the principle here. That is something to keep in mind. So, TKN, right, we know what it is going to give us, right. You have organic nitrogen and thus NH4N, let us see, NH4 or NH3N. And what is it that we are going to try to do by nitrification? This NH4N is going to what do we say, be transformed into or oxidized to nitrates, NO3 minus. But again this is a simplistic diagram, we will look at that later. And during that time obviously the organic N will be degraded by microbes to NH4, right, and then that NH4 again to NO3 minus. But as I mentioned, NO3 minus or the nitrate is toxic to humans and you do not want it to be in the water. So, you have to remove it, but again it is very soluble. What do you want to do? You want to see to it that it changes phase such that we can remove it. So, that is where we have denitrification, as in nitrate, NO3N as in NO3 minus expressed as N. So, you do not need to really look at this. Nitrate, which is NO3 minus, now is going to be reduced to nitrogen, but here the issue is this is aqueous phase and this is gaseous phase, and then this nitrogen gas is going to leave the system, let us see. So, that is something to keep in mind. But again, how is this reaction going to come about? Please note that this will not occur in the presence of oxygen. Why? We looked at the relevant electron, not electron transfer, energy generation for different electron acceptors, and you would have seen that with this particular electron acceptor, they do not gain a lot of energy. So, if there is oxygen present, the different kinds of bacteria will thrive, let us see. So, what do we need? We need a more reduced compound, let us say, organic compound, and then what is it, nitrates, which are the electron acceptors, and that is what you will have, let us see, right. So, let us look at the relevant reactions. So, biological process. So, ammonia oxidized by oxygen, but directly you will not have formation of nitrate. First you will have formation of nitrite, and this is called, or the type of bacteria that do this are called ammonia oxidizing bacteria, let us see, right. So, that is the relevant reaction, let us see. And then what happens to this nitrite? Nitrite is further oxidized by oxygen to nitrate by what we call nitrite oxidizing bacteria. Here ammonia is being oxidized, and then here we have nitrite being oxidized. So, overall though If we cancel out nitrate, this is what it looks like, but please note that we have two kinds of what do we say, reactions involved here, and we have different kinds of bacteria, let us see, right. So, here one aspect to note that here is we have no organic compound present here, right, no organic compound. So, how do these bacteria grow or such, let us say, not grow, cell synthesis, how does that occur? So, they are autotrophs, not heterotrophs, that is why they use inorganic carbon to form their cell mass, let us say, right, for production of cell mass. But for the BOD removal, the kind of bacteria that are heterotrophs, let us say, they need organic compounds for cell synthesis. We already looked at the relevant reaction. So, what are the characteristics, or how do based on this I can also figure out when to have nitrification taking place and so on and so forth. So, they are very sensitive to DO, as in only when the dissolved oxygen is high will this takes place, is it? I guess so. You need a lot of oxygen, right. So, dissolved oxygen has to be high. So, if the dissolved oxygen levels are relatively low, this nitrification and then the subsequent denitrification will not occur, let us say, right. They are highly sensitive to toxics. So, that is why if you remember in the BOD test, we add denitrifiers, which more or less means we are adding a compound that is specifically toxic to these nitrifying compounds, as in the ammonia oxidizing bacteria and nitrite oxidizing bacteria, let us say, right. So, we add compounds that are toxic to this, that is something we do in the BOD test, but again they are highly sensitive to toxics compared to the other compounds, right, and they are slower, I guess, growers, if I may say so. So, more time is required than the heterotrophs, which will do the job for organic compounds. So, these compounds which look at NH4 and such, or the ammonia, they require more time. So, HRT is typically high, let us say, right. So, time required increases in lower temperatures, that is something that we already know. So, in this case we looked at what is it now, nitrification, as in NH4 plus going to NO3 minus, right, two reactions, not half reactions. And obviously then you will have denitrification. I guess I should have another slide here before enhanced phosphorus removal. So, you have denitrification, right. So, for that what do you want? You need organic compound, you need an electron acceptor, which is what we are trying to remove, NO3 minus. So, here if oxygen is present, this will not occur, right. So, obligately anoxic. So, that is one aspect. So, oxygen is present, this will not occur, and then you need some phosphorus, and then you are going to have the relevant reaction going through. Similarly, for what is it, enhanced phosphorus removal, well, I guess typically phosphorus is accumulated by a certain kind of microbes. So, you are going to create conditions such that you have these microbes thriving, and the phosphorus is accumulated in these relevant compounds, and then they are degraded, let us say, right. So, what do we have with respect to denitrification? I guess nitrogen gas is formed. So, for enhanced phosphorus removal, we are trying to achieve accumulation of around 8%, but this we will again discuss later, let us see. There are certain conditions you need to maintain for these phosphorus accumulating bacteria to thrive, let us see, right. So, let us move on. So, we discussed activated sludge process in some detail, only some detail, we will come back to that. But let us also look at the different what do we say, treatment mechanisms which are sometimes still used in the western world or were used in India. So, oxidation ponds, let us say, again oxidation. So, you will have a source of oxygen, that is why oxidation, but they are shallow. Why? If not shallow, you are going to have anaerobic conditions, as in no oxygen conditions at the bottom, and here light penetrates to the bottom because it is shallow too, right. And then you are going to have algal photosynthesis, that again will lead to your presence of or generation of oxygen, right, algae photosynthesis, and you are going to have presence of oxygen. And around this algal system, you will also have bacteria which will use this oxygen and then degrade the organic matter to the relevant byproducts. So, depending upon the size, you can have what do we say, facultative and anaerobic zones. I think we are going to discuss this, okay. If I increase the depth, let us say 2.53 meters, what am I going to have? The light is not going to penetrate to the bottom. So, I will only have oxygen generation here, so aerobic conditions here. At the bottom, it will be anaerobic conditions, no oxygen, let us say, right. So, I am going to have anaerobic conditions at the bottom, different kinds of microbes will thrive here, but again there is a symbiosis between these three layers, but we are not going to go into that detail here, right here. But obviously, why will people choose this? Again, here you are going to have a facultative, those that can, I guess, more or less do both, let us say, if I may say so, right. Why will people choose this? As you can see here, you are not providing oxygen, so it is cheap. But why won't you choose this, especially in India? Well, we do not have as much land, and also water is a much precious resource here in India. And then if you have relatively less removal efficiency, you are not going to be able to use your relevant wastewater, right, because again the nature can't degrade your effluent, let us say, right. So, that is one aspect to keep in mind. Let us see what else I have. So, we are going to look at, I guess, microbes and how they grow, right. So, the picture that we have here is that, if this is a closed system and I provide some substrate initially, just maintain some substrate, right, very low substrate, how is it going to, how is the system going to behave? So, again substrate, that is what we have, sewage bacteria presented by this, represented by this, and then sludge bacteria represented by this. As you can see, at different times you will have different, what do we say, types of microorganisms thriving. Why is that? Let us say once certain kinds of bacteria thrive, then you are going to have the carnivores which are going to feed on these kinds of bacteria. But when you do not have these bacteria which can feed the carnivores, then the carnivores are going to die. Again, then you will have a different kind of bacteria growing and so on and so forth. So, it is cyclical, let us say. So, that is what you can see out here. We are not going to go into detail here, right. Say, let us move on. But in continuous flow systems, the earlier one was closed system, but here if it is continuous flow, as in what we experience in the wastewater treatment plants. So, what do you see here? It is a dynamic system, right. Initially one kind of what do we say, bacteria, and then a different kind. So, obviously here, as you can see, the system is pretty sensitive too, but over time you are going to try to achieve the kind of bacteria that will increase the efficiency of your relevant treatment process, let us say, right. So, what do we see have here? Sewage bacteria in the effluent, that is what we have here. So, that is going to decrease out here. Why? Because the kind of bacteria that are going to thrive in your aeration basin are going to, what do we say, eat up, let us say, or not going to create conditions that are going to favor other kinds of bacteria. For example, one aspect I remember is that fungi and bacteria, which one will grow? It depends on which one has access to more food. Bacteria being smaller have greater surface area, so they can absorb the food faster. Not the case with fungi. So, over time the bacteria are going to thrive. So, that is what you are going to see, and that is one aspect to keep in mind. So, how are they going to grow? Let us say we looked at one aspect here where we looked at it in detail, but if we look at a general case, let us say I take a closed system, put some microbes and just look at the overall microbial growth, let us say. So, let us say in this graph, let me also put in my substrate or my food waste, let us say, my waste which is the food for the microbes. So, what is going to happen? Initially we are going to have the lag phase. On the y axis we have bacterial numbers, on the x axis the time. Initially the bacteria get used to the relatively new environment. So, you are going to have lag phase, let us say, right. They are still getting used to the relevant environment. Once they are used to the environment, you are going to have an accelerated growth phase. Here different what do we say, bacteria are going to have different rates of growth, but they are going to start growing, let us say, right. And then we are going to have log growth phase. As you can see, it is linear. So, more or less the growth rate is relatively uniform, let us say, or a regular growth rate. And then stationary phase. In this, during this time, what is going to happen? All this time your substrate or the food waste is going to come down, let us say, right. So, at this point, as you can see, there is no more food for the microbes, or maybe even here. So, here the cell or dead cells itself are going to serve as food for the other microbes, and afterwards, there you have nothing there, and then you have the death phase, I guess, right. So, 4 phases: lag phase, accelerated growth, log growth, and stationary, and in general death. But in a continuous flow system, you are going to try to see to it that you provide food continuously. There will be some decay, but that is a different aspect, let us say. So, we are going to look at this log growth phase. So, this is how bacteria can what do we say, grow. I believe we have a relevant numeric or problem later. So, population, after what do we say, n number of generations, initial what do we say, population, as in 1 goes to 2, 2 goes to 4, right. So, based on the generation time you can calculate that. Let us see what we have. So, log p equal to log p naught plus n log 2. So, bread yeast cells divide and form 2 cells every 5 minutes, okay, 5 minutes generation time. So, if I initially have 10 to the power of 5 cells in a suitable environment, how many cells will I have in 30 minutes, right. So, 6 generations out here I guess. So, 30 minutes by 5 minutes per generation is 6 generations. So, p is equal to 10 power 5 initial p naught into 2 to the power of n number of generations. So, you see 10 power 5 end up to be 6.4 into 10 power 6, right, within 30 minutes. So, they grow a lot, the mass will not increase, but they grow a lot, it is the numbers that count, not the mass obviously. So, that is one aspect to note here. So, how is it that the microbes degrade your relevant substrate or our waste? You know, we are going to look at this particular equation, but we are not going to derive that, let us see. So, what do we have? We have enzyme and the substrate, right, enzyme and substrate, and then you are going to have an intermediate product, yes. So, K1, K2, forward reaction, backward reaction, and then this will go to the products, let us say, right, K3. Yes, this is what you have, and the rate of production of this what do we say, products or such, you can get it by applying this mass balance on this particular what is it, ES, let us say, right, and then you can get it, and you know, it is just let us say looking at the reactions that lead to formation. So, what are leading to formation? K1, I mean E plus S is leading to formation, and the backward reaction is leading to loss, and this reaction also is leading to loss. So, you can apply mass balance and get it, but we are not going to do that here. But more or less, if I am not wrong, R will be going to be equal to R max into S by K plus, yes, S is the substrate concentration, right, and K I guess is nothing but equal to K2 plus K3 by K1, right. Again, you can look at the relevant derivation. So, what does that tell us? Let us say, you know, what will the profile look like if this is R and if this is substrate? So, the profile will look like something like this, right, and at this point it is S when the S is high, right, and here I guess is the R max, R max. At this point R is R max, as in when S is far greater than K, what do you see? S cancel out and R equal to R max, let us see, right. So, that is what we have, and also another case when it is at half I guess, right, when S is equal to Ks, you can think of that, then it will be R max by 2 Ks I guess, right. So, again this is the Michaelis-Menten equation, right. Similar to this, people observed that, or Mr. Manu or Dr. Manu observed that, I think it was in 1949, the microbes also have a similar profile, right, profile for growth, and that is what we are going to look at. Again, the profile is similar to this, R equal to R max to S by Ks plus S. This is a constant as you can see, and S is the substrate. So, again one aspect to keep in mind, we will just discuss this later. So, what do we have? Let us see. So, Monod equation as you can see is similar to this. Let us look at what the variables are here, right. So, this is the specific growth rate, different what do we say, names. So, you can look at that specific growth rate and such. So, here mu max similar to R is equal to R max into S by K plus S. I think earlier it was Km and now it is called Ks, right. Here you have mu specific growth rate, right, is equal to mu max into S by Ks plus S. Earlier it is Km, here it is Ks, let us say. So, what is this maximum? It is the maximum growth rate constant of the microbes, as in this will tell me the new cells, mass of new cells per the cells existing already per time. So, these two cancel out and that is why units are per time, but they are more or less giving me an idea about how much new cells are being generated per the existing cells per time. And S is the concentration of the food for the microbes or our waste, that is what we have. Ks is the half saturation constant, as in when will the mu max be half, that is what we have, right. And what else do I have here? Okay, half saturation constant, concentration of limiting food when mu is equal to 0.5 mu, right. So, that is something you have, you can plug that in and see that out here. Let us see that mu is equal to mu max into S by Ks plus S. Again, this is going to give me an idea about why is this important now. I want to know how cells are growing or how the microbes are growing. So, this is what will give me an idea about how the microbes are growing. So, as was observed by Mr. Manu, and that is why we are calling that the Manu equation, we have the specific growth rate being depend upon the maximum, the food and this relevant constant out here, let us see, right. And again, I was just trying to say, when will this be the case? Let me just look at that. So, you want Ks is when mu max is equal to half. Let us see in which conditions will that turn out to be, let us say, right. If this is mu max by 2 is equal to mu max S by Ks plus S, right. Ks plus S will then be equal to 2S. As you can see, this is the case when Ks is equal to S. That is what we also looked at in this case out here. This was supposed to be Km, I guess, right, Km. So, that is what we have. So, why is this important? Let me see what we have out here. You know that in general, when we have A plus B going to C plus D and rate constant is K, the rate of this reaction is equal to rate of reaction, rate constant times concentration of A and concentration of B. Similarly, here if I want to look at the growth rate of microbes, I am going to say, as we mentioned, we are going to look at the concentration of microbes, we are going to express by R. What is it going to be depend upon? It is going to be depend upon the concentration of the microbes right now. So, X, they are increasing, right, and the rate constant I can assume it to be this, right. So, dx by dt equal to mu times x, let us say. Mu is the growth rate constant, mass of new cells per mass of total or existing cells per time, let us say, right. So, that is what we have out here. So, this will give me the rate of growth of the relevant microbes, let us say, right. So, what is this going to turn out to be? We know that mu is equal to mu max into S by Ks plus S into X. So, that is your rate of growth of the relevant microbes, right. Let us move on. Manu equation, there are limiting cases here. One is when we have a lot of food, S is far greater than Ks. So, when there is a lot of food, obviously, the food is no more a limiting factor for the microbes. It is not dependent upon the relevant Ks, as in when S is far greater than Ks, we can neglect Ks and then SS cancel out, then mu becomes mu maximum. That is what we have out here. So, it is only dependent upon the amount of cells, but if food is less, right, if food is less, right, say if it is far less than or S is far less than Ks, right. So, what is going to happen? Mu is going to be equal to mu max into S by Ks, right. So, it is then very much dependent upon the food and its first order, right. That is what we see, and these are the two limiting cases out here. So, bacterial growth, as we saw, are R net. R net is going to be dependent upon rate of growth of the bacteria and also rate of decay or death of the bacteria. So, here we already developed the equation for rate of growth, which was equal to mu times x, that is what we have out here, and death, that will also have a rate constant, decay, endogenous decay rate constant into the concentration. So, that is what we have. This is the R net, let us say, right, considering the bacterial growth and the death, let us say, right. So, let us move on. So, bacterial growth and death, let us say. So, why am I concerned with this bacteria? At the end of the day, I am not here to feel philanthropic and have a lot of bacteria. It is because I want to degrade the waste which I am representing by S. But what is S going to be dependent upon? As we know, it is going to be dependent upon how many bacteria are there, let us say. So, the rate of removal of S will depend upon the rate of growth of the relevant bacteria, right. So, here we have two aspects. So, rate of growth of rate of growth of the microbes will be related to the rate of loss of the substrates, right. But both are not going to be the same. Why is that? It is not so efficient, the process is not so efficient. You have relevant electron transfer, let us say, and such, let us say, right. Again, there are other aspects, so it is not going to be as efficient. So, that is why you are going to have a variable here which we call the yield coefficient. What is the yield coefficient going to give you an idea about, right? Let me see if I have that right. So, here they are representing Rs by ds by dt, negative because it is being lost, right. Rate of growth of microbes dx by dt, and 1 by y they are bringing it out here, right. So, rate of growth of microbes, we are going to have a fraction out here. What is this fraction called? It is called the yield coefficient. Decimal fraction of food mass, food, that is converted to food converted to biomass. As we know, not everything will be converted, right. Some of it will be used up for energy and such, only some will be used up for or converted to cell synthesis or for cell synthesis. So, that is why you have this less than 1 yield coefficient. So, this yield coefficient is nothing but milligrams of biomass for the milligrams of food utilized. So, that is what you see out here. So, from here I can calculate how much my the rate of my loss of substrate is, right. So, rate of substrate loss is equal to 1 by y, rate of growth of the relevant microbes, and negative because it is being lost. So, what do I have? I know that minus 1 by y into, depending on what equation you are using, you will have this, let us see, right. So, dx by dt we already looked at that there. So, rate of growth of the relevant microbes, let us say, which is nothing but mu times x, right. So, mu times x, what is mu? Mu is mu max into S by Ks plus S. So, rate of growth, that is equal to minus mu times x by y, and because we know that mu is equal to this particular equation, we end up here, right. So, that is what we see. Again, you do not need to mark anything up. Let me just summarize and end this session for today. So, what are we trying to do? I am trying to understand how microbes grow, and what is the equation that tells you about it? It is the Monod equation. And what is this depend upon? It tells you, or what is it depend upon? This growth rate or specific growth rate, which we are saying is a constant. It depends upon the substrate, let us say, how much food is there, right. So, that is what we know, which is nothing but mu max into S by Ks plus S. And from that we can calculate how the microbes are growing, rate of growth. Why is that important? Because we know that the microbes grow by breaking down our waste. So, we can relate our waste loss to the rate of growth of the microbes, but not all the waste that is being degraded will turn into the cells of the relevant microbes, right. So, you are going to have a fraction that is called y, or the yield coefficient, right. So, with that I will end today's session, and in the next session we are going to look at understanding how to design the system. But how do I design the system? As in, I know how much food is coming in, so I will have to design how much waste can be degraded within a certain time, as in the time required, and then the volume of the tank, and then how much microbes I am going to have to maintain in the relevant tank, right. So, with that I am going to end today's session, and as usual, thanking you for your patience, I bid adieu.